Algorithms are the backbone of computer programs, and understanding their performance is crucial for developing efficient and effective software. So, two critical performance matrices here are time and space complexity, which describe the behavior of algorithms as the input size increases. In real world terms, think of a recipe for baking a cake. Now here the time complexity of the recipe would be the total time required to bake a cake, considering factors such as mixing, baking and cooling. And the space complexity of the recipe would be the amount of storage space needed to write down the recipe, including the list of ingredients and instructions. So in both cases, the complexity grows proportionally to the number of ingredients and the length of instructions, making time and space complexity valuable tools for evaluating and comparing recipe. So today we will simplify both time and space complexity using real life examples that demonstrate time and space complexity in a relatable way. So let's get started with what is time complexity. So basically this time complexity is a measure of how much time an algorithm takes to solve a problem as the size of problem increases. In other words, is a way to estimate the performance of algorithm as the input size grows. So imagine you have a to-do list with 5 tasks and you need to decide which one to complete first. You can sort the tasks based on their priority level with the most important task at the top. This is a simple example of an algorithm with low time complexity. So in this example, the time complexity is linear ON, which means the time it takes to sort the task increases proportionally to the number of tasks n. In other words, if you have 10 tasks on your list, the time it takes to sort them will be roughly twice as long as sorting 5 tasks. On the other hand, if you had to write out each task on a separate piece of paper and rearrange them manually, so the time complexity would be quadratic, that is ON square. This means the time it takes to sort the task increases at the rate that is proportional to the square of the number of tasks. For example, here sorting 10 tasks would take 100 times longer than sorting 5 tasks. So to summarize this, we can say that algorithms with lower time complexity are more efficient and faster as they can solve larger problems in less time. And this time complexity is an important consideration when designing algorithms, as it helps you understand how well an algorithm will perform as the size of problem grows. Next comes the Python code for time complexity. So this is a simple Python example to demonstrate linear time complexity ON. In this example, we are creating a list of integers or the numbers and then iterating over that list to calculate the sum of its elements. The time it takes to perform the iteration increases proportionally to the length of list, that is n here. So in this example, linear time sum function iterates through the numbers list, adding each element to the total variable. Now here the time it takes to complete this operation increases linearly with the number of elements in the list, and the time complexity of this algorithm is ON, which means the running time is directly proportional to the size of input list numbers. Then comes space complexity. Now the space complexity is a measure of how much memory an algorithm requires to solve a problem as the size of problem increases. It's a way to estimate the amount of memory an algorithm needs to solve a problem regardless of the hardware it is running on. So imagine you have a to-do list with 5 tasks and you want to keep track of which task you have completed. You can write each task on a separate sticky note and move the notes to a different pile when you finish a task. This is a simple example of an algorithm with low space complexity. So in this example, the space complexity is linear ON, which means the amount of memory required to track the task increases proportionally to the number of tasks n. In other words, if you have 10 tasks on your list, you would need twice as many sticky notes as when you had 5 tasks. On the other hand, if you had to write each task on a separate sheet of paper and move the sheets to a different pile, the space complexity would be quadratic, that is ON square. This means the amount of memory required would increase at a rate proportional to the square of number of tasks. For example, tracking 10 tasks would require 100 sheets of papers. So to summarize this, we can say algorithms with lower space complexity are more efficient and require less memory, making them more suitable for problems with larger inputs. And the space complexity is an important consideration when designing algorithms, as it helps you understand how much memory an algorithm will need to solve a problem. Then comes a Python code for space complexity. So here is a simple Python example to demonstrate linear space complexity, that is ON. So in this example, we are creating a list of integers, that is numbers, and then creating a new list, that is squared numbers, to store the squared values of the elements in the numbers. So here the amount of memory required for squared numbers increases proportionally to the length of this numbers n. So in this example, linear space squares function create a new list squared numbers and appends the squared values of each element in numbers to this new list, and the amount of memory required for squared numbers increases linearly with the number of elements in numbers. So the space complexity of this algorithm is ON, which means the amount of memory required is directly proportional to the size of this input list numbers. Thank you.